Alright, today we're learning about 11.3 diffraction. Diffraction is when light passes through a small slit and most of the light goes straight through and until it hits a screen, creating a central bright fringe in the middle. But around the edges of the slit, light will diffract at an angle, at any angle, and all angles. If we draw a slit diagram like so, with 3 parallel lines of light going into it, all diffracted at the same angle, and say if this angle is theta, and this distance here from the top of the first, from the point of diffraction to the top, from the top of the first light wave, the ray, down to the bottom of the bottom ray is theta, is lambda, sorry. And the slit width from here to here is b. Yeah. So okay, if this distance here from where the point of diffraction starts here to here is lambda, a phase difference between each wave will be 1/2 because theta over 2 is 1/2. Lambda over 2 is 1/2 lambda. Because of this 1/2 lambda, this means there's destructive interference. This means that when the waves are appearing on the same screen here, they will appear in such a way that they will cancel each other out in a sense. They're out of phase. So what these two waves create, because they're out of phase and out of phase by 1/2 lambda, is just a straight line in the middle. And this creates a dark fringe on the screen where there's no light at all. If the light is then diffracted at an angle of 2 theta, the distance between the top and the difference in wavelength between the top and the bottom rays will be 2 lambda, sorry. And with this, destructive interference again occurs. And so on the screen here there is a dark fringe, but there is no light being reflected. If we draw the triangles for each of these diagrams, where this is the slit width b, this is the distance lambda, and this is the angle theta, and again the same with 2 theta, and 2 lambda, we can see then, due to small angle approximation, where tan of theta equals sine of theta equals theta, that theta, as it is the opposite over the adjacent here, in other words tan of theta, and due to small angle approximation, theta equals lambda over b. For this diagram, we can also see that due to small angle approximation, 2 theta over 2. We can see with this diagram also that due to small angle approximation and the use of tan, that 2 theta equals 2 lambda over b. Therefore, as this is multiplied by 2 at the top, we can therefore prove that theta equals lambda over b. As we saw before, when the light passes through a slit, it creates a central maximum where the light is most intense, as the light is just passing straight through. If we plot this against theta, the angle of diffraction against the slits, and with this being the intensity of the light, we get a large central maximum, like so, and then small, dipping down to 0 intensity, where the first dark fringe is created. After the central maximum, it goes down to the first dark fringe, then up to another maximum, down, touching the bottom line again, where intensity is 0, and carries on this pattern until intensity, as theta nears infinity, reaches 0. This is reflected on the other side as on the same theta, but on the opposite direction. So the first dark fringe is also creating no intensity, going up, going down, creating no intensity and lowering until theta is infinity and intensity is 0. We can use this to create to solve problems. If we have a small slit like so, and a screen here, say, and this is the width of, let's call it y, of the central maximum, the slit width being b, the length between the slit and the screen being L, we can find out using this formula and basics of trigonometry using sine and tan, and due to a small angle approximation, these just equaling theta, we can find the distance here, or L, if we need to.